What you're looking at behind me is the front face of this building, which is made of a what we call URM. It's an unreinforced masonry building. It has no steel reinforcement in the structure. And this is the primary problem with buildings of this class. They were built a long time ago. They don't have any steel in them, and so therefore they are structurally deficient by today's codes. The process being used by Syntec and by my firm is we are drilling holes. As you can see today, that's what they're doing up there. They're drilling holes that go vertically down through the wall, and inside those holes they're going to insert structural steel tubing, which will then be sealed with a concrete material. I'm going to walk over here and show you a sample of the steel. This is the structural steel. This is a high-strength steel, a grade 50 steel. It's a square tube. You can see that the tube is all a continuous length. There are no welds in the tube. It's a solid piece of steel. Each tube could weigh 10 to 20,000 pounds, which is why we have this crane. The crane is used to help us with all of the operations on this project. The crane is used to do the coring, to lift out the whole material. The crane is also used to lift the steel and place the steel inside the hole. This site also sits on a soil condition which we call a liquefiable site. A liquefiable site is a site where if it's exposed to water, the soil liquefies and it accelerates the earthquake vibrations on the building. We call that liquefaction. In order to deal with the soil condition, we have to install deep piles. The pile depths are 40 feet. That means 40 feet, if we take the elevation where I'm at right now, the 40 feet is measured 10 feet down because we have a basement. So we're actually going 50 feet from this sidewalk vertically straight down. We're using a steel pipe pile. This is the fitting on the pipe. The pipe is an 8-inch circular diameter, and it's cut in 10-foot segments, 3/16 of an inch thick, grade 50 steel. We can't take long pipe and put it into the basement because we wouldn't have enough clearance. So we have to insert the pipe in 10-foot segments, and we bolt them together as we drill. Inside the core of the pile, we put high-strength concrete, 5,000 psi concrete, and we fill the hole. These piles are installed. There's 32 piles. They're going in all around the perimeter of this building. In order to put the pile in, we are rotating the pile and advancing it with what's called a helical anchor. On the end of the pile is a helix. This is the tip of the pile. On the end of the pile is a bolt with a fitting, and inside this is a helix. That rotates this pile, and it's driven into the ground like a screw. And that's how we deal with the liquefaction problem. So we have a soils problem, we have the unreinforced masonry issue, we're dealing with the liquefaction using these pipe piles, we're dealing with the URM by using the insertable tubes. This is something that has never been done before on any project. This is the first of its kind, the first time using this type of a structural system. It is approved by the City of LA, but it is the first application of this type of method. Okay, we're going to talk a little bit about the project, the African American Unity Center, and I want to go over some of the technical explanations and also some of the structural engineering theory that we're utilizing on this project, some of it which is somewhat unique and relies on some basic principles. So to start off with, let's try to make a few definitions clear. The essence of a shear wall is designed for loads in its plane. So we have in-plane shear loads which run within the plane of the wall. These are called in-plane loads. If we draw ourselves an axis, a z-axis, an x and a y-axis, The in-plane loads are running in the plane of the wall. So we can have in-plane, in this case along the x-axis, these would be called shear loads. If the loads are coming in vertically, those are also in-plane loads, but those are axial. So we have in-plane loads, shear loads, and in-plane axial loads. Then we have out-of-plane loads. Out-of-plane loads are, of course, occurring out of the plane of the wall. So we have a shear wall which has a certain length. It has a certain height. And these are the definitions of the loads. And so we go back to our diagram of our shear wall, where we have a wall which is accepting loads both in plane and out of plane. When we say unreinforced, it means that it does not have, this means that there is no steel. And normally we like to have steel in these walls because the steel helps to take those loads, the loads that we were looking at earlier, axial loads, in-plane shear loads, out-of-plane bending loads. But when we don't have steel, then there is no steel present. If we put the wall through a shear load, and this is now looking at the face of the wall, this produces a bending moment at the bottom of the wall, which will cause cracking. And it will also create what's called diagonal tension cracks. Diagonal tension cracks occur at 45-degree angles to the horizontal. And when a wall is subjected to that, it will produce cracks, shear cracks. If the wall is stressed in the out-of-plane direction and it's unreinforced, then the stress occurs along the plane of the thickness. And if I redraw this diagram, looking at it from the end cross-section, and I have an out-of-plane load, or let's use the term W, then I'll develop bending cracks. If the wall is stressed out of plane and it's too much, the wall could crack and it could topple over. Well, what are we saying when we say that we're going to seismically retrofit a URM building? Well, what we're saying is, number one, we're reducing. Now notice the important word there. We're reducing. We are not eliminating. We can never eliminate potential risk of a building collapsing. Number two, we're enhancing. In other words, in simple words, i.e., we're making it stronger. Now the question is, how do we do this?